In this video, we will talk about making inferences or conclusions about two proportions. We'll discuss the methods for testing a claim about two proportions and constructing a confidence interval estimate of the difference between two population proportions. Remember, though, that when testing a claim about the population proportion, the p-value method and the critical value methods are equivalent. The confidence interval method is not equivalent to the p-value method or the critical value method. The notations we are going to be using for the population 1, we will use sub 1, and for the population 2, we'll use sub 2. P sub 1, p hat 1, n1, q1, which is equal 1 minus p hat 1, and x1, and corresponding notation for the population 2. The pooled simple proportion is denoted by p bar, and it combines the two simple proportions into one proportion and is shown in the following formula. The idea of a pooled proportion is that if we say have simple information from two populations that have the same proportion, we would use both samples individually to estimate population proportion p hat 1 and p hat 2. But if both samples come from population with the same proportion, why would we do that if we can just use the pool proportion? The requirements for testing a claim about two population proportions are that the sample proportions are both from two simple random samples, the two samples are independent, and for each of the two samples, there are at least 2 successes and at least 5 successes and 5 failures. That is, NP hat is greater or equal 1 and NQ hat is greater or equal 5. For test of hypothesis made about two population proportions, we consider only tests having a null hypothesis P1 equals P2. Test statistic is calculated by this long, scary-looking formula, but the good thing is that we don't have to memorize this formula because p-values are automatically provided by technology. If technology is not available, then use table A2 of the standard normal distribution. And to find critical values, we also use table A2. Remember, a critical value is the score, z-score, t-score, or chi-square score that separates critical region from non-critical region. Let's do the following example. Connecticut and New York are contiguous states, both having laws that require front and rear license plates. The proportion of Connecticut illegal cars with rear license plates only is 239 out of 2049. So 239 cars in Connecticut had the rear license plates only out of 2,049, or it's 11.7%. The proportion of New York illegal cars with rear license plates only is 9 out of 550, or 1.6%. The sample percentages are 11.7% and 1.6%. They are different, for sure, but are they significantly different? We will use a 0.05 significance level and the p-value method to test the claim that Connecticut and New York have the same proportion of cars with rear license plates only. First, check the requirements. The two samples must be simple random samples. We cannot trust the author on that, Maria Tirola, who collected these samples. The two samples are independent because the cars in the samples are not matched or paired in any way. And let's consider a success to be a car with a rear license plate only. So for the Connecticut, the number of successes is 239 and the number of failures is 1,810. So they're both at least 5. For New York, there are 9 successes and 549 failures, and there are both at least 5 as well. The requirements are satisfied. Same steps of the hypothesis testing procedure we previously applied to conduct a hypothesis test for one population. If you don't have this table, feel free to stop the video and copy it down.